Prove by induction, part 3. Prove by induction that the sum of r squared from r equals 1 to n is equal to n over 6 times n plus 1 times 2n plus 1. This formula is using this sums up the squares of natural numbers from 1 to n. For example, if I want to sum up 1 squared plus 2 squared plus 3 squared plus 4 squared, in this case it will be 1 plus 4 plus 9 plus 16. 1 plus 4 is 5, 5 plus 9 is 14, 14 plus 16 is 30. So the sum of the square numbers from 1 to 4 is 30. I could use the formula to also do that by writing 1 over 6, where n is 4 as the maximum number. So that will be 4 times 4 plus 1, 4 plus 1, times 2 times 4 plus 1. And that will be equal to 4 times 5 times 2 times 4 is 8 plus 1 is 9 over 6. You can see how many 3 goes here? 2. How many 3 goes there? 3. How many 2 goes there? 1. How many 2 goes there? 2. And that will be 2 times 3 times 5. And that equals to 6 times 5, which equals to 30. So we got the same value in doing it this way or using that formula here. So now we need to show that first thing to do is to show that the statement is true for n equals 1. That is the proof by induction. So we have to look at the left hand side and the right hand side. So for the left hand side and the right hand side, we need to write that the left is going to be, we're going from sum of 1 because n equals to 1, r equals 1, r squared, and that would be 1 squared, and 1 squared is 1. For the right hand side, we need to use the formula here. That would be 1 because n equals 1. Remember, n equals 1 over 6 times 1, that's the n, times 1 plus 1 times 2 times 1 plus 1, and that will be equal to 1 over 6 times 2, because that's 2 here, and this is 2 times 1, which is 2 plus 1, 3. So that would be times 3, and that would be 6 over 6, which equals to 1. Therefore, we've just proved the statement is true for n equals 1. So we always have to look at left-hand side and then look at right-hand side. This is the left-hand side here and the right-hand side. If that is equal to 1, then that's good. So step 2, we need to assume the statement is true for n equals k. So now we rewrite this equation and replace n with k by transforming n into k, and then we write k in place of n, which is 1 over 6k, open bracket k plus 1, close bracket, n plus 1, open bracket 2k plus 1, and that's all we need to do. Part 3. We need to prove the statement is true for n equals k plus 1. And to do that, this is the equation here we got, and we're going to transform that. We're expecting to put n equals k plus 1, but we're going to write it as n equals k plus 1 here. That will be equal to n equals k plus 1 squared, the last term. This will be the last number squared. So that will be from r equals 1 to k, and then plus the last term. So this is what we have to do. And if we substitute n equals k plus 1 here, this is our final goal. So that is what we need to get. From this expression, we need to get this. Therefore, we now need to, which equals to, so this one here and that will be now replacing that with that, but instead of n, we write k. This is what we did in step 2. So we bring in step 2 in. So now we replace n with k from step 2 plus the k plus 1 squared. And so now what we now need to do is take a common factor out, which is k plus 1. There's a k plus 1 here. There's a k plus 1. Now we get 1 over 6 k plus 2k plus 1. Then we have k plus 1 left. And then we want to take 1/6 out. So we get k plus 1 over 6, we're going to get 2, open bracket, 2k plus 1 plus 6k plus 6. Because if I multiply this by 1 over 6, that will become k, because that will be 6k over 6 and 6 over 6. So that will get back to that. And we need to expand this one here and form a new expression. So when I expand that, add on to this, I get that. K times 2k is 2k squared. K times 1 is k plus 6k, that's 7k, and plus 6. I need to factorize this. When I factorize this, I get that. And that's k plus 1 over 6. Factorizing this, I get k plus 2 times 2k plus 3. So finally, I got what I was expecting. That if I replace that with k plus 1, which is, it will give me this. And when I use this, I get that. So that one is being proved, that n equals k plus 1. So finally, step 4, I need to write this for statement. 1. Since the statement is true for n equals 1, has to be written. And if this statement is true for n equals k, which we've proved, then it is true for n equals k plus 1, which we just derived. And therefore, the statement must be true for all value of n greater than 1 or equal to 1. So therefore, this for statement has to be written.